Right, in this video, we're going to talk about suggested homework problems from section 3.6. Let's go ahead and get started with number 5. We're going to match the graph of the function with the graph of its derivative. So 5 is a constant function. It has a negative slope. I'm looking for a derivative here that has a constant negative number. That's d. So 5 is d. 6, we have increasing, then decreasing with undefined in the middle. So let's look for that. Increasing positive slope, then decreasing negative slope here, undefined in the middle. That looks like C for 6. 6 is C. 7 is, that looks like a cosine function, so its derivative should be a sine function. That looks like A. And then 8 has to be B because we're matching. And that makes sense to me that we're approaching vertical negative slope there, and we have a local maximum there, so we're going to go through 0, and this is increasing. It's positive here, so that makes sense. All right, let's move on to number 9, where we'll actually do some math. Here we're going to analyze this graph and sketch a graph of the function. My sketches are going to be just that, sketches. So we want to identify any key points like intercepts and extrema, points of inflection, and then as well as any asymptotes that we may be able to label. So 1 over x minus 2 minus 3, we're going to have let's see, over x minus 2 minus 3 equals 0, when 1 over x minus 2 is equal to 3, 1/3 is equal to x minus 2, 2 1/3 is equal to x. That's 7/3 is x. For my x-intercept, we have 7/3 0. My y-intercept is going to be 0, negative 1/2 minus 3. So negative 3.5 is negative 7/2. Okay. Let's see, asymptotes. Vertical asymptote at x is equal to 2. Horizontal asymptote at y equals to negative 3. This constant that's sitting out here, since this part can never be 0, I get close to negative 3, but don't get there. Anything else? Shouldn't have any minimum or maximum points with this. Let's prove that. Y prime negative 1 over x minus 2 squared. That's always negative. Y prime less than 0 for all x, so no critical numbers. And then second derivative is equal to 2 over x minus 2 cubed. Y double prime is less than 0 for x less than 2. Y double prime is greater than 0 for x greater than 2. So with all that information, I should be able to somewhat sketch here. There's no point of inflection because there's nowhere where the second derivative is equal to 0. The sketch here at 2, there's a vertical asymptote. At negative 3, there's a horizontal asymptote. And then we have the points 2 1/3 0, so right there. And then we have y is -3.5, so right there for our y-intercept, and so this is going to be down here. This is going to be up here, and I can prove that with limits if I would like, that the limit of y as x approaches 2 from the right is going to be 1 over 0 from the right minus 3. That's going to approach positive infinity. Limit as x approaches 2 from the left of y is 1 over 0 from the left minus 3. That's going to negative infinity. Limit as x goes to positive infinity of y is equal to 0 minus 3 is equal to a -3. And that's a number that is a little bit bigger than -3 here, because this is a little bit bigger than 0. And limit as x goes to negative infinity, y is equal to 0 from the bottom minus 3 is -3 from the bottom here. And that's our first problem where we were sketching a graph. There's my sketch. See how I'm concave down on that piece and concave up on this piece with no extreme values. And I have my asymptote here, y equals to -3, and my asymptote here, x equals 2, labeled. And I have my x-intercept of 7/3 0 and a -7/2 0 labeled. All right, let's look at number 13. 13 says y equals x plus 1 over x squared minus 4. So there's an x-intercept at -1, 0 when I set the numerator equal to 0. Vertical asymptotes, when I set the denominator equal to 0, x is equal to plus or minus 2. Y-intercept is going to be 1 over -4, -1/4. So that gives me a 0.0, -1/4. Y prime is derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. So y prime is x squared minus 4 minus 2x squared minus 2x over x squared minus 4 squared is a -x squared minus 2x minus 4 over x squared minus 4 quantity squared. And so potential critical number when x squared plus 2x plus 4 is equal to 0, squared plus 2x is equal to a -4. Half of 2 is 1, 1 squared is 1, and I get x plus 1 squared equals -3, and there's no solution to that. So there's no min or max here. From that, there's just the vertical asymptote. And if I want the second derivative here, then that is, well, let me double prime equals a derivative of the top, negative 2x minus 2 times x squared minus 4 squared minus derivative bottom 2 times x squared minus 4 times 2x times a negative x squared minus 2x minus 4 all over x squared minus 4 to the fourth. Y double prime will be really gross. Let's see, we have a negative 2 and a x squared minus 4 that will come out. And this leaves me with x plus 1 times x squared minus 4, then plus 2x times negative x squared minus 2x minus 4 over x squared minus 4 to the fourth. So one of those comes out. Y double prime is a negative 2 times x cubed plus x squared minus 4x minus 4 minus 2x cubed minus 4x squared minus 8x over x squared minus 4 to the third. And y double prime is a negative 2 times a negative x cubed minus 3x squared minus 12x minus 4 over x squared minus 4 to the third. Y double prime is 2 times x cubed plus 3x squared plus 12x plus 4 over x squared minus 4 to the third. And I will need to use my calculator to figure this out, but y double prime is equal to 0 when x cubed plus 3x squared plus 12x plus 4 equals to 0. There's no way that I'm going to factor that, or I don't have a nice cubic formula that I know in math to take care of that. So let's pull up the calculator here and share it right here. So let's change this to this view here. And we have x to the third plus 3x squared plus 12x plus 4. And I need to graph that and find the 0 here. Second calc, 0. And I can't read that. My answer for x is about negative 0.36. So point of inflection when x is about negative 0.36. So sketch a graph here, and we have -2 is an asymptote, a vertical asymptote. +2 is a vertical asymptote. We have a horizontal asymptote at y equals 0 if I didn't say that, because degree of the top is less than degree of the bottom. So y equals 0, x equals 2, x equals -2, x-intercept at -1, 0, y-intercept at 0, -1/4. And as we approach 2 from the right, this is positive and positive. This is going to go off to positive infinity. I have no x-intercept over here to cross this asymptote, so I'm going to be staying above this axis here, like so. When I approach 2 from the right, that's a positive number. I'm sorry, from the left, this is a positive number over a negative number. So that's going to go to negative infinity. I'm going to cross through and cross through again, and probably come up this way is what it looks like. So this piece looks almost like a cubic shape here. As I come at -2 from the right, that's going to be a negative in the denominator and a negative in the numerator. So that's going to go to positive infinity. And when I come at -2 from the left, that's going to be a positive in the denominator and negative in the numerator. So this is going to negative infinity, never crossing the x-axis. So it's staying down here in this area. And there you go. So even though we're not drawing the graphs so much on the calculator, we are going to need the graphing utility sometimes to help us find zeros or points or minima or maxima or points of inflection that are irrational numbers. So let's see now, we were done with number 13 there. On to number 25. Y is equal to x cubed over the square root of x squared minus 4. So domain here is that x has to be less than -2 or greater than 2, so that I don't have a negative inside of the square root. So 0 is not in that domain, so there's no y-intercept. For that reason, there's also no x-intercept, because it looks like the x-intercept would be 0, but that part of the graph isn't there. So let's see if there's minima or maxima. Y prime is 3x squared root x squared minus 4 minus over 2 root x squared minus 4. 2x up here, 2's will cancel. This is all over x squared minus 4. So we're going to multiply top and bottom by root x squared minus 4. I get y prime is equal to 3x squared times x squared minus 4 minus x over x squared minus 4 to the 3/2 power is equal to 3x to the 4th minus 12x squared minus x over x squared minus 4 to the 3/2 power. Y prime is x times 3x to the 3rd minus 12x minus 1 over x squared minus 4 to the 3/2 power. And should be I forgot to multiply by x cubed here. So that should be x to the fourth. And that should be 2x to the fourth minus 12x squared. And that should be 2x squared times x squared minus 6. That's looking better. So I have critical numbers, not 0, because that's not in the domain. Let's see, root 6 is bigger than 2, so yes. Plus or minus root 6. Negative root 6 is smaller than negative 2. Positive root 6 is bigger than positive 2. So let's look at my number line here that I have asymptotes at -2 and 2, and there's the graph does not exist in here. That's not in the domain. And then I have negative root 6, have positive root 6 over here. So be helpful to pull up the calculator again for the sake of evaluating the sign of these things. So my function alpha y equals n over d 2x squared times x squared minus 6 all over x squared minus 4 raised to the 3/2 power. Table setting ask, and let's delete these. So let's pick something less than negative root 6, like -3. And that's going to be a positive number. So positive in this interval. And then something between -2 and negative root 6. So I'm going to choose -2.1. And that's going to be a negative number. And then this section does not exist. I'm going to choose a positive 2.1. And that's going to be a negative number. And then something bigger than root 6, I'm going to choose 3. That's going to be a positive number. So there's a local max here, and there's a local min here. Now, if I go back and stick those numbers into the original, I have y of negative root 6 is going to be negative root 6 cubed over square root of negative root 6 squared minus 4 is negative 6 root 6 over root 6 minus 4. It's negative 6 root 6 over root 2. Root 6 divided by root 2 is root 3. So this is negative 6 root 3. Do 6 root 6 over root. Okay, so we already said decreasing on this interval and increasing on this interval. and decreasing and increasing. Let me just go ahead and confirm that this is correct with my calculator, that if I have y is equal to, clear this out, x to the third divided by square root of x squared minus 4, that if I put in bars, y bars, function y1 of negative root 6, let's check that against and what did I say that was? I said that was negative 6 root 3. So let's see, negative 6 root 3. Okay, same thing. So just make note over here, relative max at negative root 6, negative 6 root 3. And then we're going to have a relative min. This is an odd function. So I already know this is going to be root 6 and then 6 root 3, because it's going to have reflection, negative x, negative y. Since it's an odd function, I don't even have to calculate that one. So let's go ahead and sketch my graph. Let's see, what else should I write down over here? No x-intercept. No x-intercept, no y-intercept. Domain is from negative infinity to negative 2, union 2 to infinity. We have the first derivative. I guess I should get the second derivative and test for points of inflection. Let's see if it happens here. Derivative of the top, 8x cubed minus 24x times x squared minus 4 to the 3/2 minus derivative of the bottom 3/2 x squared minus 4 to the 1/2 times 2x times 2x to the 4th minus 12x squared over x squared minus 4 to the 3rd. So this is 8x times x squared minus 3 x squared minus 4 to the 3/2. That would be a 2 that comes out of there and cancels with that. 3x squared minus 4 to the 1/2. And another 6x to the 3rd. I pull that out. X squared minus 6 or x squared minus 4 to the 3rd. All right, and then we have a 2x times x squared minus 4 to the 1/2 that can come out of everything. And this is 4 x squared minus 3 x squared minus 4 minus 3x squared, x squared minus 6, all over x squared minus 4 to the third. So when I take that 1/2 down, this is 2x 4 times x to the 4th is 4x squared minus 3x squared plus 12 minus 3x to the 4th plus 18x squared over x squared minus 4 to the 5/2. That is 2x times 4x to the 4th minus 16. Oh, hang on, that is 7. 4 times 7 is 28x squared plus 48 minus 3x to the 4th plus 18x squared over x squared minus 4 to the 5/2. It's 2x times, that's a single x to the 4th. Negative 28 plus 18 is minus 10 x squared plus 48. And that's over x squared minus 4 to the 5/2. So this is 2x times, and then are there factors of 48 that add up to be 10? 1 and 48, 2 and 24, 3 and 16, 4 and 12, 6 and 8, and it goes to 8 and 6. The smallest sum is going to be 14, so no, that doesn't factor in to rationals. I can tell you from the graph of this that there's no points of inflection. I really have no point in going forward here, but let me go ahead and graph this for you and see if this is ever equal to 0. Let's put this over here for a second. Y equals x to the 4th minus 10x squared plus 48. Let's graph that. Zoom 0 so you can see the graph. Zoom out. And let's zoom box right here to make sure that it never crosses the x-axis. That's what I'm interested in. Zoom box again. Right, so it looks like it potentially crosses there and there. Let's calculate if there's a 0 there. There's not. And second, calc 2 over here, there's also not, since it's symmetric. I'll just prove to you that there's no 0 in this interval either, staying above the x-axis the entire time. Okay, so no point of inflection. Right, so no point of inflection, and I have, I don't really need to know concavity here. All right, did I get, yes, I did. So vertical asymptotes, x is equal to plus or minus 2. Again, degree of the top is bigger than the degree at the bottom. I should have a quadratic type oblique asymptote. So I'll just, there's no nice way to figure that out with pre-calculus or calculus other than to just evaluate that this is x cubed over x essentially. So it's going to mostly model x squared over something. We know we don't have this inside part of the graph here. As I get close to 2 from the right, this is getting close to a positive, small positive number in the denominator. That's a positive number in the numerator. This is going to positive infinity up here. And I have this point here that is root 6, 6 root 3. If I again want to look at that number, that's 10. So 2, 3, 4, 5, 6, and then 10 something. It's way up here. So we're going up here and then turning, and then it's going to be somewhat quadratic looking on that piece. And then this is 2, 3, 4, 5, 6, and way down here somewhere for where it's going to turn. Why did I say 6? It's root 6. Root 6 is 2.5 something, so it's right. It's way up here though. Then it turns and it has kind of this, it's not going to approach a line. It's going to start increasing that way. And then negative 2.5 roughly, and then negative 10, and it's down here and it turns. And it again has that quadratic feel. So this is negative root 6, negative 6 root 3, and this is root 6, 6 root 3 up here. And I can't label an oblique asymptote, a slant asymptote, but I can label this is x equals negative 2. This is x equals 2. There's no horizontal asymptote, no intercepts. Let's move on to the next one. Number 35 says that we want to, there's no graphing with this one, I don't think, is there? Yes, there is. X, y squared is equal to 9. So if xy squared is equal to 9, then that's y squared equals 9 over x. And we just might want to get some points here. That means 9 over x always needs to be positive, which means that x has to be greater than 0. My domain is 0 to infinity, and my range here is going to be negative infinity to 0, union 0 to infinity. Y can take on any value. When I take plus or minus the square root, other than this value can never be 0. So I'll have a horizontal asymptote at y equals 0. Vertical asymptote x equals 0. Horizontal asymptote y equals 0. And this is going to have x-axis symmetry since it's y squared. So let's look at what the top half would be of y is equal to 3 over root x, or y is equal to -3 over root x. Let's graph this piece first and then use symmetry. So x equals 0, y is equal to 0. Let's graph some points here of at x equals 1. This is 3. This is 1, 3. Next thing that I have a perfect square is when x is 4, I have 1 and a half. And then when x equals 9, 5, 6, 7, 8, 9, y is 1. So I have this curve. It's going like this. And I should be able to mirror that. -1, -2, -3, -4, 5, so on. So this is 9, -1. This is 4, -1 and a half. And this is 1, -3. So this comes this way. And I'm not going to have any extreme values. You can see that from the graph. I could try to prove that with the derivative by implicit differentiation, but I don't think that I need to do that here. Also not going to have any points of inflection here to worry about. That's not even a function of x. So sorry, that was 35. I'm going to do 37 next. 37 now tells me to analyze the graph of the function. F of x is equal to 2x minus 4 sine x on the interval 0 to 2 pi, 0 and 2 pi are included. So I'm not going to find x-intercepts without my calculator for that, because I could find a y-intercept, that f of 0 is going to be 0 minus 4 times 0 is 0. So this y-intercept, I know it's 0, 0, which would also make it an x-intercept. I would have maybe some interesting stuff happen at the zeros of sine, maybe, that I would want to take into account. So other interesting points here are going to be x is pi, and y is 2 pi, or x is 2 pi and y is 4 pi. At pi over 2, that's probably a minimum, because this takes on its maximum value and I'm subtracting the most from there. Let's prove that with a derivative though. F prime of x is equal to 2 minus 4 cosine of x, and let's set that equal to 0. -4 cosine of x is equal to a -2. Cosine of x is equal to 1/2. So x is equal to arc cosine of 1/2 is going to, and then the other answer will be 2 pi minus arc cosine of 1/2 will be my other critical number. So this is cosine is 1/2 of pi over 3. And then it's going to be 2 pi minus pi over 3. So that's 6 pi over 3 minus pi over 3 is 5 pi over 3. Okay, so those are my critical numbers here. I want to look at 0 to 2 pi. I have pi over 3 and 5 pi over 3. Then if I stick in to the derivative here, a number between 0 and pi over 3, like pi over 4 or pi over 6. Let's go with doesn't matter. Let me use my calculator to help me. So 2 minus 4 cosine of pi over 4. Make sure that I'm in radian mode. I am. And that is going to be a negative number. Then I want something between pi over 3 and 5 pi over 3. So I'm going to go with pi over 2, which gives me a cosine value of 0. So this is going to be positive. And then something bigger than 5 pi over 3, I'm going to go with 11 pi over 6. So 4 cosine of 11 pi over 6. That's going to also be negative there. So that gives me a local min at pi over 3 and a local max at 5 pi over 3. So this is going to be pi over 3, and then f of pi over 3 is 2 pi over 3 minus 4 times the sine of pi over 3 is root 3 over 2. So 2 goes into there 2 times. This is 2 pi over 3 minus 2 root 3. And this is my min. And my max is going to be 5 pi over 3. F of 5 pi over 3 is 10 pi over 3 minus 4, and then sine of 5 pi over 3 is a pi over 3 reference angle, but it's a negative value, so it's a negative root 3 over 2. It's 2 and 2. Negative times a negative is a positive. This is 10 pi over 3. So 10 pi over 3 plus 2 root 3 for my local max. And I'll probably have to do some decimal approximations for that to be able to draw the sketch. So let me just put this data over here to help me. Y-intercept 0, 0. X-intercepts are, I don't know, without the graphing calculator. I'll try and find them in a second. Local min at pi over 3, 2 pi over 3 minus 2 root 3. Local max at 5 pi over 3, 10 pi over 3 plus 2 root 3. Let's see if I need to find points of inflection. I do. So that makes my second derivative equal to 4 sine x. That equals to 0 when sine is equal to 0. And I'm not interested at the endpoints. Those won't be points of inflection, so the only thing in the middle there that will be a point of inflection is when x is equal to pi. And so that's going to be f of pi is equal to, I already figured that out, that's going to be 2 pi. So point of inflection, pi, 2 pi there. All right, let's use the calculator here to approximate some x-intercepts if I need to. I do need to, so original function, this kind of defeats the purpose because I'm not supposed to be graphing it on the calculator if I'm sketching the graph, but I have to because this is a number that I can't find without the calculator. So let's zoom trig here, and then second calc, 0, and I have an x-intercept at negative 1.8 something, but that's not in my domain because I have to start at 0. So second calc 0 of, and then let's see if there's one that is, I know that's going through 0, 0 there. That's my x and y intercept. Interested in this one over here, and it looks like 1.895, so about 1.895 approximately. All right, so there's all my work. I'm going to clear this to make the sketch now. And 1, 2, 3, 4, 5. 1, 2, 3. I actually don't even need this side because it's restricted. 1, 2, 3, 4, 5. 1, 2, 3. 1, 2, 3, 4, 5. All right, so we know it's going to go through 0, 0. It's going to go through pi over 3 something. So pi over 3 is a little bit bigger than 1. And then it's down here. Okay, so down there somewhere. And then we're going to go through 1.8 something is over here, 1.9. And then at pi, which is roughly there, we have a point of inflection, x-intercept. This is my min. And then I have a local max at 5 pi over 3, which is not quite at 2 pi. So 1, 2, 3, 4, 5, 6. We're back here a little bit. And then this is up here. This is just a rough sketch. So this goes down and then turns and comes back up. And then down. And then this is still this kind of a shape. I'm going to do my best to make it that shape, and then it turns the other way. And that's the high point, and it comes back down and for a little bit, and then it stops at 2 pi. And This is, again, my approximate x-intercept there of 1.8 something something. All right. So not a perfect graph, but you get the idea that of what's going on here. And let's see, do I have another one? I have one more. I know this takes a long time to do these problems. I apologize for that. We've actually got a couple more. I'm going to graph that one on the calculator for you. It's right there. I'm going to go from 0 to 2 pi here and let you see what it thinks the graph should look like. And we again should have this shape that goes down, up, down, like that. If I zoom out a little bit, you'll see that. So this little piece right here that's going down, up, down, right here, that's the piece of the graph that I'm interested in. But it's got that little thing where it's adding x to it, so that's why it looks like it's based off of this line here. All right, number 43. 43 says g of x is equal to x tan x on the interval from negative 3 pi over 2 to 3 pi over 2. So let me just go ahead and kind of sketch a graph of this. I know I'm going to go through 0, 0. I know that the asymptotes of tangent are odd multiples of pi over 2. So pi over 2, negative pi over 2, 3 pi over 2, and negative 3 pi over 2. Normally, tangent has a graph that looks like this. And so I'm going to use that to my advantage here. All right, so in this piece, I'm going to have a positive x value times a positive y value. That's going to stay positive. It's going to grow faster here, and it's going to go up that way. Now I'm going to have a negative x value times a negative y value, so that's also going to be positive, and that's going to come up this way. Now I have a positive x value times a negative y value here, and so that's going to be negative. And then I have a positive x value times a positive y value, and that's going to be positive, and it's going to go up and even faster that way. And then this is going to be a negative x value times a positive y value is going to be negative, so that's down that way. And a negative x value times a negative y value is going to be positive and go up this way. So there's kind of my sketch of my graph. I should use calculus to figure out where these intercepts are. The zeros of tangent are going to be at 0, and then this is going to be zeros of sine. So that's going to be negative pi and positive pi there for my x-intercepts. And I have vertical asymptotes. Let's see, y-intercept at 0, 0. This is negative pi 0, 0, 0, pi 0. Vertical asymptotes at negative 3 pi over 2, negative pi over 2, pi over 2, and 3 pi over 2. No horizontal asymptotes here. I wanted to find the derivative of this to talk about increasing and decreasing. G prime of x is equal to tan x plus x secant squared x. I really don't think that helps me find anything to know what the sign of these things are. It was just easier to talk about a positive divided by a negative. And so I know that I have this local minimum right here. These pieces don't have a minimum or a maximum, so my only critical number is going to be when x is equal to 0. That's a local minimum because I'm decreasing and then I'm increasing. I can see that on my graph right there. Points of inflection will be at negative pi 0 and at pi 0 will be where my concavity changes there, from concave up to concave down and from concave down to concave up there. So already those are interesting points that I've already found. Really no need to find them again with derivatives. Let's move on to 55, I believe, is the next problem. This one's really challenging because it doesn't have an equation, it just has a graph. I'm going to do my best to show you what this is going to be. So it's kind of a sinusoidal function, but it just doesn't line up on the asymptotes at all. So it goes kind of like this, or it doesn't line up on the axes at all, is what I was trying to say. It's like that. And this is supposed to be y prime, so, or f prime. F prime. So they're asking, what is the potential graph of f? If this is my slope function, and my slope is, this is going to be something that is going to be kind of related to cosine, but it's going to be negative and still negative with a so right here, there's a, let's see if these are lined up here. So right here, there's a 0 of some kind that I'm interested in. And right here, there's a 0 of some kind. So this is where my local minima and maxima are, right? And then right here is where there's a point of inflection somewhere. So point of inflection, min max, min max, and 0 of this is another min max, and another point of inflection right here. All right, so I'm going to maybe make this the maximum right here, and then the minimum right here, and a point of inflection somewhere in between, like this, and then another point of inflection and a maximum, something like this. It looks like a sinusoidal graph. Again, that's kind of awful looking. Second derivative here to kind of line up with this is that there should be a 0 here, and there should be a 0 there, and a 0 there, and this should be concave down, so this should be negative between these two zeros right here should be negative, and then this should be concave up here, like that, and then concave down again, and so like that. And so this is a potential graph of f, this is a potential, or this is f prime, this is a potential graph of f double prime. And again, I hope that that's multiple choice for you on WebAssign, because it's really hard to just sketch that by hand. All right, 59. I think this is going to wrap it up. Sketching a graph of a differentiable function that satisfies the condition x equals 2 is the only critical number. F prime of x is negative for all x less than 2. F prime of x is greater than 0 for all x greater than 2. Limit as x approaches infinity. F of x is equal to 6. Limit as x goes to, this was negative infinity. This is positive infinity. F of x is also 6. So we have y equals 6 up here is an asymptote. Have x equals 2 is going to be a turning point, and I'm just going to say that this is probably going to do something like this, because I don't know any better. I'm going to try that first and get close to that asymptote there. Now, for less than 2, the slope is negative, and it is. Greater than 2, the slope is positive, and it is. Doesn't say anything about concavity there, so I'm good. This is a potential graph there for number 59. I don't have an equation for it, but I'm sure you could find something to make a model kind of like that. All right. Again, sorry this one was so long. The next one won't be nearly as long. It's just kind of difficult to do. Curve sketching, you have so much you have to find for each problem. More than likely, though, since you're doing your homework and maybe even taking your test through WebAssign, hopefully you get some sort of matching or multiple choice for some things there. If you're taking your test in class, then hopefully your teacher is going to give you some simpler functions than some of these, where you can just graph a pretty basic polynomial or rational function or something like that. That's the type of thing that you graphed in pre-calculus. But you just do all the calculus to find all the minimum and maximum values. And they may be weird numbers that have square roots, cube roots, something like that. You just might need to get decimal approximations of those things as best as you can. Or maybe the teacher will design the problem so that all the numbers for the critical numbers and the points of inflection and all that come out to be nice numbers. Hopefully that happens to you. All right, next time we'll come back and we'll talk about section 3.7. See you for the next video.